All right, in this presentation, you're going to learn a little bit more about the register names used in assembly language. And they're kind of crazy, and it has to do with the history of the Intel processors. And so we're going to look at that a little bit. Now, after this presentation, I'd like you to go ahead and do ASM Activity 2, which is in the folder called 2-close-examination. All right, let's get into this a little bit more. Now, I've been showing you this abstract view of the computer, and we want to keep this in mind with our CPU over here on the left and our memory over here on the right. And the way this CPU operates is it's executing instructions. This thing called the program counter contains an address of the next instruction of the code over here that should get executed. And so each instruction is executed one after the other, and the lines of the assembly code correspond to each of those instructions that's going to get executed. Now, what we're going to start looking at very carefully right now is the names of all these registers that you're going to see in the assembly language. Now, these names have historical context. So you remember that before break I talked about these different versions of the Intel instruction set, what these assembly instructions look like. And so Intel started out with basically 16-bit processors. And so the word size was 16, and the instruction set was called x86-16, and then it went to x86-32, where the word was 32-bit size, and then finally today we have x86-64, where the word size is 64 bits. And what this means is, in this historical context, the register sizes increased in width. And so they started out with 16-bit registers and then 32-bit registers, and now we have full 64-bit registers. But we actually can access the 16, the 32, and the 16-bit register names. And in fact, we can even access half of the 16 bits, so single bytes. And we're going to see how that works. And so this means that because of backwards compatibility, we have register names for all three versions of these instruction sets. And so it gets kind of complicated, but we're going to try to get through this. And then you're going to always want to have a reference of all these register names because there's a lot of them. All right, so here's the 64-bit register names, some of them, not all of them. So you remember we've been seeing a little bit of code where registers like %RBX and %RDX and %RAX here are being used in this code. Well, here's all of the here is some of the 64-bit register names, not all of them. But you see here that here's RAX, here's RBX, RCX, and so on. We'll learn why the ABCDSIDI in a little while here. So the ones that start with R are 8-byte wide, are full 64-bit. These ones here that start with E are 4-byte wide registers, and those get used for certain types of data. So, for example, ints are 4 bytes wide. So you'll see in assembly code that matches C code that uses ints, you'll see these ones that start with E being used. Now, the complication is that if you access these other ones that happen to start with numbers, so with x86-64, they added these extra registers, and they just started using numbers instead of these different sets of nomenclature here. And so so there are some that just have numbers after the R. And then to complicate matters more, they switched from using an E in front to using R8D to represent the 4-byte wide registers here. So again, you're just going to want to have a reference in front of you, and in a minute I'll tell you which table that is in the book that you'll want to have available to you. So for some history now, x86-32 only had the E's. They didn't have the R's because the E's represent the 4-byte wide registers, and they were considered these general purpose registers. There's these two that end in SP and BP that we're not going to use. You won't see them in code examples in the next few activities or in your homework. These are used for different purposes when when functions get called. And so we won't be using those. So these are 4 bytes wide for the 32-bit x86 32-bit registers. And so that's where these names came from. But then there's also 16-bit registers that came from x86 16, and those can be 2 or 1 byte wide. And so the 2-byte wide register names, they're half of the 4 bytes, and those names look like this. So in the assembly code, if something that only needs 2 bytes is used, then the compiler will use these register names instead, so getting rid of the E, basically. And so originally in x86 16, these were the names of the registers, and then when they needed 32-bit wide ones, they added the E, basically. Now you can access single bytes, and we'll see examples of that later on. And the names of those, each of the 2 bytes have different names. And the H and the L here, I think, mean this is the lowest order single byte, and this is the highest order second byte of the 2 bytes here in the original x86 16 register names. So that's a little bit of the history, and you will see all of these names used. So for 4 bytes, the E's will get used, and so integers, for example. And then if you're using a short, these names will get used. And if you're using chars, you'll see these names get used. And so these will show up in some of the code that you looked at. Now, the origin of these names, the A, C, D, B, A was originally supposed to be holding an accumulator. And C was supposed to hold a counter. D was supposed to hold any data. Base was the base of an array, so basically the 0th element of the array. And then an index off of that base, whether you were putting it into another array for a destination or a source. These just really are not used anymore because our programs are far more sophisticated, and the compiler uses them for all sorts of different purposes now. And so these are really obsolete names. Now, these, the stack pointer and the base pointer, those are still used quite the way they were originally designed when we're using function calls, so when we're going from one function to another. But we're going to skip that for now, and so you won't see the use of these two either, and that's why they're there in red. All right, so that's the historical context of all of this. Now, in your code, you're going to see all of these different register names. So out here is our 8-byte wide ones, corresponding 8-byte wide ones here, all with the R in front of them. And then you will also see the 4-byte wides are these with a D after them for these ones with numbers. And then the 2-byte wide ones have a W after them. And the 1-byte wide ones have a B after them. And so I haven't shown them all for 9, 10, 11 through 15. They all look the same. They have a W and then a B after them. And so what you really want to do is look at figure 3.2 in the book for all of these register names. Mark that page in your book. If you have access to a copy machine, you might want to make a copy of it and have it. I have it marked in my book all the time to go refer to all the various register names with their widths. And so that's a very handy table. All right, so now let's go back to this again. We've just been looking at all the names of the various registers in the central processing unit, or the CPU. And now we're going to think a little bit about your program that holds the data for every variable that you've declared in the program, along with the code. And then the instructions that the CPU executes operate on register values and data in memory, and they move the data between memory and the registers and back and forth. And so that's why this arrow here is going both ways. It's like data can move from registers to memory or from memory over into the registers. So a lot of the different operations that you might do, such as adding two numbers, those require the data to get moved from memory into the registers in order for the add to be done. The CPU instructions for arithmetic operations require that the data is in registers first. And so we're going to look at this move operation next, because this is used all the time in order to get our data first over into registers and then do some arithmetic on them. So here's the move operator that you'll see in assembly code. And it requires both a source and a destination. Now I've shown an abbreviated set of the register names over here, where these are the R and E ones, the 8-byte and 4-byte ones. And then here I've shown the 8-byte ones, where N, of course, is 8 through 15. And so now what we're going to start thinking about is what this move operation is doing and what our various source and destinations can have in them in particular assembly instructions. So one little word here, the move is followed by, so MOV is followed by a letter. The Q stands for quad word, which also means 64 bits or 8 bytes is going to be moved. So what that means then is that the destination and the source, one or the other, is going to be one of these R registers because we're going to be moving a full 8 bytes of data. And then that source or destination is then going to be one of these register names. These are for types such as pointers, so you might move pointers around. You might actually put pointers into a register. And for longs, because long values are 8 bytes. Now, a double, even though it also is 8 bytes, those are treated a little bit differently. So we don't use a Q for that. We aren't going to look at the floating point assembly language operations because they get kind of complicated. So we're going to skip those as well. We're just going to look at integer values. So now move could be followed by an L, which stands for long word, because in x86 16, W was for word. And so once they went to 32 bits, they called that a long word. And so 32 bits, that's what the L means. So 4 bytes. So any types in our C code that are ints, for example, you'll probably see a move L, and you'll also see either the source or the destination use these register names, because these with the E are the 4-byte register names. And too bad it's R and Q and E and L. It would have been nice if these matched up better, but they don't, so it's something you're going to have to get used to and remember. Now, you might see move W, which is the original historical 16-bit word, or 2 bytes. And so those also will show up for variables like shorts. And so that long word, or L, is the 32-bit values for 4 bytes. All right, so now let's think about the types of operands here, these source and destination operands. We're going to be moving data from one place to another, and we're going to think about the various values that source and destination can take on. So one thing that a source or a destination can be is a constant. And so most often we'll see this as the source, but sometimes you'll see it as a destination. So anyway, a constant is just a number. So it's just a number like a C constant you would have in the C code, but it's prefaced with a $sign. These operands can also be registers. So one of these 16 different register types here is typically what's used. And so here's a couple examples, RAX or R13. As I was pointing out before, RSP is reserved, so we won't see that. And some others are used for particular instructions, but you won't have to worry too much about that. Now, the other type of operand, a source or a destination, is memory itself. And in order to indicate that we're moving something from memory, we use these parentheses in the assembly language. And so every time you see parentheses as a source or a destination in the assembly language, that means we're moving from memory. And in this particular example, this register RAX must contain an address pointing to memory. Now, we will see more sophisticated uses of this called addressing modes a little bit later on. So let's look at some of these combinations of source and destination for these three. So which combinations are actually valid? So we can move from an immediate, a constant, into a register or memory. So in that case, here's an example. So we can move a constant value, hexadecimal 4, into register RBX, for example. Now, the C code that does this might look something like this. So we take a variable temp1 and we set it to this constant. And so in this case, when this C code line was compiled into this, the compiler writer was saying, okay, from now on, RBX is going to contain temp1 until I don't need it anymore. That's how we can read that. And so the next type is we could take a constant and we can move it directly into memory. And so here now what we've done is we've assumed that RAX contains an address back into our data location for our program in memory. And these parentheses again are indicating that we're going to go and put this constant back into memory where this RAX is pointing. And we might have some C code that looks something like this. So in this case, P is a pointer. And this is called pointer dereferencing. I'm going to talk about this again later. The idea here is that this star in front of this pointer says use a value. So what we're doing is we're taking this constant and we're putting it in the place that P is pointing to. We'll describe this more later also. So the other thing that we can do with a move is we can move from a register to a register. And that is shown like this. So that's a very simple one. And C code, we might have had something like this where we take one variable and put it into another variable. We can also take what's in a register and move it back into memory. And so that looks like this. So again, here is the parentheses that are showing that we want to take whatever value is in this register and we're going to move it back into the memory location that the register RAX is pointing to. And so in this case, this is similar to what we had up here, where now maybe RBX contains this register, contains the value for temp2. And so now what we're saying is take what's in temp2 and put it back into memory where P is pointing. All right, so the last kind of move that we can do is from memory into a register. And so that looks like this. So here, the source is memory, and the destination is a register. And again, the parentheses are telling us that that source is from memory and that RAX is pointing to a location in memory. And so that looks like this, where we're going to now take P, which is a pointer, we're going to dereference this, and we're dereferencing it to say, let's get the value that P is pointing to in memory, and let's put it into this variable called temp2. And now in assembly, temp2 is now in this register RDX after this instruction would get executed. Now it's important to note that you can't do memory to memory transfer. So you notice here, source and destination cannot be memory. It's either register to memory or memory to register. Okay, so now we're going to look more carefully at this particular variation right here, where the source is a memory location. So this is the simplest type of addressing mode as well, just a set of parentheses with a register in it. And then register R specifies a memory address. And so whenever you see this in your assembly code, what it means is we're going to go to memory and we're going to take what's in register R as an address. So we're going to look at this address in memory and grab that data as a source and send it across. And so register R contains an address. We're going to go to that address in memory and we're going to get a certain number of bytes. And the number of bytes we're going to get depends on whether it was a move Q. That means we're going to get 8 bytes. A move L, we would get 4 bytes. A move W, we would get 2 bytes. Okay, now this type of memory addressing mode corresponds directly to this pointer dereferencing that I was talking about earlier. So here's another example. XP is a pointer. This star in C means that we're dereferencing that pointer. It's kind of a strange term, but you'll hear it all the time when you talk to C programmers. And we're going to get the value that address XP is pointing to, and we're going to put it into this variable T0. Okay, so this is done a fair amount in C code, so you're going to want to get used to it. You can do what's called this dereferencing of a pointer. And now you'll note that this star XP, the use of star here for pointer dereferencing, is on the right side of this assignment. It could be on the left, so we can have it go both ways. And it's different than having declared this pointer in the first place. So here is how we declare that pointer. Now, the travesty of C is that this star is used in these two different ways. So it gets very hard to read when you're first learning C code. But remember, a declaration looks like this. It's got a type in front of it. Here in this code, when it's on especially the right-hand side of the of this assignment, that star in front of XP is saying, go get the value that XP is pointing to. All right, now this C code line corresponds to an assembly line that looks like this. And what's happening here is that RDI contains that XP pointer, which is an address. So this register contains XP. We're going to use that to go into memory, and we're going to grab the value in memory. In this case, it's going to be 8 bytes, and we're going to put it into the register named RAX. And so from this, we can infer, because of this memory addressing here, that this part corresponds to this pointer dereferencing over here in this C code, and that now RAX is going to hold this value T0 when this instruction gets executed. So you're going to, in your activity, you're going to comment on lines of code like this. And what you may want to do is you may want to put the line of code that matches this to the right over here as you're doing your commenting. And also note this sort of thing, that now RAX holds the value T0. That can get helpful as you're learning to decipher this code. And so that's what I'm going to suggest that you'll want to do as you're working on the activity. Now, so this activity is going to be in 2 close examination. I'm going to give you just a few more things about this code just to get you started so you can really follow and be able to begin to start stating what's happening with each of these different assembly instructions and matching them to the C code. In this case, this line of C code matched this line of assembly. That doesn't always happen, and we'll see some examples of that later. In this close examination, they're pretty much one-to-one, so you won't have to worry about that as much. We'll introduce the slightly more sophisticated code in the following activity after this one. So one thing that might be really helpful to you too is to look at section 3.4.3 of your book. There's a sidebar in there that says new to C, which talks exactly about this pointer dereferencing. And so that might be another source for you to look at to try to understand this. There's also on Moodle in the resources section some links to information about C pointers, so you could look at that as well. All right, so now in activity 2, what you're going to do is you're going to examine this function called swap. And what you want to start being able to do is to comment each line of this function and see what's going on. So now remember in our abstract picture here of our computer, the registers now I've written over here on the left, and we're going to have data being held in memory for this particular function. Now, the declaration of this function is like this. Swap takes in 2 variables, a long pointer and it called XP and another long pointer called YP. And so somewhere over in memory, XP is pointing to a long that's 8 bytes wide, and YP is pointing to a long that's also 8 bytes wide. So that's how we interpret that. Now, this is a declaration saying that XP is a pointer as opposed to the dereferencing. Okay, so here they're declaring these to be pointers. All right, so now what's happening is that there's a very important thing that you're going to need to remember here when you look at all of these functions from now on. These 2 variables, by convention, are placed in very particular registers. And so by convention, the first parameter is always put in RDI. And the second parameter is always put in RSI. So you're going to have to be eventually putting this to memory. And I'm going to even give you some little hints about how you can do that. But for now, we only have 2 parameters in this function you're looking at. And the first one, XP, is in RDI, and the second one is in RSI. So as soon as the assembly gets started, these exist. So these 2 pointers, XP and YP, are in these 2 registers. So this is a really kind of key idea that you're going to need to keep in mind in order to understand what this assembly code is doing. So now the first line of the actual swap program looks like this. And here is the corresponding assembly line of code. And so now you remember RDI contains an address, a pointer called XP. And so that's pointing to some memory here. And so this particular instruction, when it is executed, when it's completed, the bytes of data over here in memory for along are moved into register RAX. So now T0 is in RAX. That's how we interpret this particular line of C code and its corresponding assembly code. Now the next line in this file, in the C code, is this, and it corresponds to this assembly line, where now RSI, it contains the XP pointer. So when this is done executing, the data, the 8 bytes that YP was pointing to are moved over into the RDX register. So this is the destination for that data. So I've given you some information here now about where these first two lines of, what these first two lines of code are doing. And so next, I want you to, in the activity, go on and continue this process for the rest of the instructions. And it might be helpful for you to use a picture like this. So after each one, you color code it or something. Or I'm also just suggesting that you can do this with comments in the code. And so here's what I'd like you to do is go to this activity. When you're writing your comments in your code, write the matching C code line in a comment next to the assembly line, and also write what variable a register contains. So for example, RAX holds T0. Now you might want to go back to the other folder to recall what the makefile is doing if you've are interested or have sort of forgotten way back when we did this first one. So have at it, and when you're done with that, you'll be able to come and view the next presentation.